Hello everyone and welcome to module 7 of the DevOps course. Today we are going to look into the first part of module 7, which is performance tuning concepts and a little about server security and firewalls. So whenever we are trying to put up a box in production, we are concerned about its security. We don't want people to be hacking into the box or looking into it. Okay, so there are a few very simple steps that one has to follow in order to convert your unsecure box into a secure black box. Um, which no one should be trying to access, or rather even you wouldn't have access to that. But that's in the extreme cases. Why do we need it? We don't want people to be messing up with the things in production because we are automating everything. So if the machines are being spinned up automatically, the logs are collected centralized, users are not present there because we don't want users to be present on the dynamically created machines. So if there is no requirement of you being there, machine should not allow you to be there, right? uh, Not only just you, maybe some another user or the person who has got access to your network, he's trying to steal something. In that case also your machine should be secure from such attempts. So we will be talking a little about performance tuning. That means if you think that your machines are not performing well, what could be the target area that you want your sysops people to fix. So today's session is going to be fairly theoretical one, except for the hands-on exercise on the firewall section. Let's talk about performance tuning first. So it comes to performance, we are not the people who would be tuning the operating system for ourselves. Rather than that, we would be the people who would be figuring out what the problems are and asking the sysops teams to get the machines running according to those things. So performance is distributed onto four different parameters: CPU, memory, disk, and network. So these are the four concepts based on which your performance would vary. How fast your CPU is performing, how big your memory is it leaking out to the disk, or if it is a secondary storage, how big it is, how fast it is. And of course, on the network side, are there any packets being dropped? Are all the devices properly connected? Is there any latency time which is coming in? What is the packet transfer speed and the throughput of the particular device? So these are the concepts that have to be taken care of. But of course there would be different teams to help you out with that. There would be maybe a CCNA team or networking team for setting up the routers and switches. We are not the people who would be going on field and doing all these things together. Then there would be a team responsible for provisioning the machines initially, so that virtual machines can run on top of them. So we are not the people who would be physically setting up the things. We would be only interested in running the cloud environments. Either it would be a private cloud or the public cloud, whatever it is. We would be using our configuration management systems to configure the stuff. So when it comes to the physical part of the side, that means the ops part of the side, configuration and tuning has to be done with the help of sysops teams. So I'll go through the problems that would be coming in with all these different sections and how do we fix it, what would be the pain points of it. Okay, and where can you seek help from your sysops teams, that this is the parameter you need to tune it. So that's the only role that you're playing. So let's talk one by one. First is the CPU. So here CPU, when you calculate the percentage of CPU usage, you don't actually calculate the time, you calculate the CPU cycles. Okay, so CPU cycles are used for calculating percentage of CPU running any of the processes. Okay, so if that is the one, that the CPU cycles would be distributed according to a small flowchart. So it would be if it is a kernel process, okay, or it's a user process. Even before that, we would be interested in knowing whether the CPU is running a process or not. So let's say the processes are either active or they are dormant. If the process is active, then the process could be either kernel process or a user process. If it is a kernel process, in that case, it would be calculated as system time. If it is a user process, it would be calculated as user time. Now, from the dormant processes, either the process is not running at all or it is waiting, right? So either it is not running or it is waiting. Both of the states are different. When you say that it is waiting, that means after the wait is finished, it would run again. So it would be placed in the ready queue. Currently, it is placed in the waiting queue, waiting for some IO to happen. Not running, the process does not exist. It is present on the disk somewhere as a binary. Now, if it is not running, in that case, the time is calculated as system idle time. And if it is waiting, then it is calculated as the wait time. Okay, so that depends in which particular state the system is running and the processes are. Initially, the process number one, which is the init process, runs as a system process. Any of the other processes where you are having the user names attached to them, in that case, it would be the user process. Now, every process is waiting for some another process to take hold of the CPU. CPU is a serial resource. It is not a parallel resource, except in a few cases. Now these days we are having multi-core CPUs, but if you consider one single core, it is still a serial resource. Okay, what I mean by a serial resource is that let's say you are running a one core CPU and you have got 100 different processes. At the front end, you would be having an illusion that all these 100 processes are actually running in parallel. So you could talk to your friend, you could listen to songs, you could interact with the UI at the same time. But at the back end, the processes are given to CPU so fast that they are scheduled in a time slicing manner. So within a second, the process might be getting itself executed 1,000 times. So that creates the illusion. So things are happening so fast that human eye cannot make out the changes between them, or the differences between the different time slots. Well, that is good, but what about the performance of the CPU? What kind of processes can we have to have best of the CPU performance? Well, there are two things. Either the process would be taking a lot of cycles or CPU cycles. In that case, we could call it a performant one, the process performant one. And either it would be switching the CPU a lot of time. That means context switching happens. And when the context switching happens, that hurts the CPU cycles. So context switching is a phenomena when you switch from one process to another process. So let's say the number of processes that you are running on a particular CPU, that also hampers the performance, of course. If you have 400 processes running, so out of the 400 processes running, let's say the first process just finished its turn on the CPU. Now next time the first process would run, it would actually have to wait for its turn. And that would be the case when all the processes are having the same priorities, of course. So I consider that all the processes are given an equal share and equal priority. So if process number A finished now, finished as in the turn finished, then the CPU would start executing process 2, process 3 until 400 processes execute. And after that, your process 1 would be queued again. Well, your system is still performant. Your CPU is still performing at whatever speed you have bought it, maybe 3 gigahertz or something. That's nice. But the process one actually has to wait for a lot of time. So the wait time for process one includes the running time for all the 400 processes plus the context switching that is happening. Now in the context switching, very first the CPU takes a snapshot of existing process. So whatever process it is executing, it would take a snapshot of it. It would dump the snapshot to the local cache. Okay. Afterwards, it would load another process snapshot. So let's say B was already running, but we have kept B in queue again because the time slot given to B has finished. So when the time slot finishes, CPU takes a snapshot of whatever the memory is required by that particular process, shifts it to the cache, then dumps it. That means dumps it to the cache, then loads another process. So similarly, for the previous process, CPU must have stored some snapshot somewhere. Okay, so it would load it. Now it is stored as a stack, of course. So it would load from the stack, and again it would start executing. So that is what happens. And doing all these things, the CPU would be spending a few CPU cycles as well. So it's not that CPU would not spend the CPU cycles. Even if it does the housekeeping activities as context switching, CPU will have to spend some CPU cycles to performing these operations. And of course, these are also programs. So between two program executions that are executed by you or system, in that case, between two program executions, all these things happen. So let's say if your program is getting 100 CPU cycles to run, that means the time slot that is given to a particular process is 100 CPU cycles, and this context switching is taking 50 CPU cycles altogether itself, then you are actually wasting 50% of your time. Okay, 50% of the process execution time, which would be almost 33.33% of the total CPU cycle time, doing nothing, which is not a fruitful thing. Okay, so context switching hurts. A lot of context switching does hurt. So depending on how many processes you are running, you might have to limit the number of context switching that is done. Well, of course, this is at the operating system level, and at the general level, you don't have to worry about context switching a lot. It starts worrying you once you have more than 400 plus processes on a CPU, which is 4 core. That means 100 processes per core, it is going to hurt you. Okay, so what do we do? Very first thing that we do is limit the processes. The number of processes that are executing on your CPU at a given point, you'll have to limit that. Okay, so how do you limit it? The thumb rule that we have taken care of since beginning, one service per machine. We don't want any extra services to be running on board. Another thing is remove any of the services that are not used. So on a machine, on a production system, we just need SSH server to be running, right? And apart from that, we need firewalls, and we need the service for which the machine is created. Maybe web server, maybe database, maybe DNS, maybe DHCP, or any other thing. So any other service which is present apart from the ones which do not uh, uh, tell you what the machine is about. Let's see, if it's a web server, then you need to have web server running. Apart from that, everything should be scrubbed off. So that would limit the number of processes that you are having, and would reduce the turnaround time for a particular process. The waiting time for the process would be reduced a lot. Now another thing that you want to take care is that the process should not go a lot into the waiting queue. If the process is doing a lot of IO, in that case also it would waste a lot of CPU cycles just waiting for the process to finish its wait time. Maybe you are running just one single process on the machine or on your VM. Other processes would be the housekeeping processes. You at least need 40 to 45 processes bare minimum on a bare minimum system, which would be taking care of the daily routines. Something like memory management, process management kind of thing, user management systems, whatever are going on in the background, they need that. But for your process to execute, you'll have to increase the priority of it if you want a really high performance systems. Now on the priority basis, there would be two different concepts of priority. One of them is called priority, another one is called the nice value. So let me get up a machine here. So I'm spinning up a box so that I could show you these values. Priority values would be ranging from 0 onwards, so this is a positive number, whereas the nice values would be ranging from -20 to +20. Any of the machines would be having some priority, any of the process would be having some priority values and some nice values. If you have multiple processes running at same priority, in that case, nice value would be helpful in distinguishing which has to be executed first. Okay, this screen is not coming up. So the nice values, when it ranges from -20 to +20, the negative nice values means that the process is less nice. What does it mean by less nice? It means that process is greedy for CPU and it is less nice towards the other competing processes. So CPU would be giving more priority to the process which is less nice. Generally, all the processes would be having a nice value of 0. You can increase or decrease the nice value according to your requirements. We would be talking about the nice values and priority values along with some other stuff in the last class where I would be covering different utilities that we are going to use. We connect to this machine. If you're on a machine, try to hit the command called top and you would be having some fields here. So out of this field, the third field and the fourth field represents your priorities and your nice values. So this process here, which is having a nice value of -20, is actually less nice to other commands or other processes. And if you see, it is K worker, that's the kernel worker, which needs to have the highest priority. Okay, that's the reason it is running at at the nice value of -20. The priority is 0, nice value is -20. So it means that the process would be having the greediest nature possible. So -20 in nice is the greediest nature which is there. Okay, on the other hand, the processes would be having more number of priorities. Let's say the top command that we are executing, this the server that we are executing, the SSH server, will all be having more priorities than the normal. Of course, we want user processes to be having more priority than the current kernel process or system processes, because we want system to be running in the background but the user process should be running in the foreground with high performance. That's when priorities are important. But when you try to balance it using priority and nice values, that's when you can hit a nice sweet spot. Okay, now talking about the next part, which is the memory. Now, memory would actually cause some problem when not decided over early. Any of the machine that you would be running would be having a limited amount of memory resource, and memory resources are split in different levels. So different levels would be the cache level. Very first it would be the registers, then the local cache, that means the CPU cache rather. Then there would be the primary memory, which is of course your RAM. Then the secondary memory, which may or may not exist. So that is the external memory pool. Maybe something like Redis if you're using it. Then there would be your storage, of course, which is disk. Okay, so your registers would be very close to CPU, and the bits that you can store in the registers can hamper the performance or enhance the performance. So these days, people are using 64-bit instruction set. So the registers are having 64 bits of storage. Moreover, there are multiple number of registers which are present in the CPU itself. So CPU can take care of instruction cycles much better these days. In older days, there were limitations on how many registers could be shipped along with the CPU. Again, the CPU cache was a problem back then. CPU would have been coming with a local cache of 64K or something like that. These days, we have got CPUs which are having up to 8 MB or even more than that of local cache. Now, local cache consists of all high performant RAM. So it is not the dynamic RAM or DDR RAM, it is the static RAM. So which is more costly, cannot be, is actually not used for primary memory because of the cost issues and the power requirements of it. But that's the more faster version of the dynamic RAM that is available these days in the market. In our laptops or on the desktop boards or even in the data centers, the RAM that we use is actually the DDR RAM. Okay, so it would be a DDR3, DDR4 version, whatever you are using. When it comes to the CPU cache, it is generally the SRAM. Okay, not even SD, it would be S specifically. So it is more faster than a primary memory. It would be comparable to the CPU cycle speed. Okay, so that's the fastest place where the CPU can access the things. If the data is not found in CPU cache, we have a page fault. So page fault is a concept where the data is not present in the first pool where you are trying to search. If it is not present there, in that case, it would be looked onto the next stage, which is the primary memory. If it is not present in the primary memory, then you could decide where to look for it. Either you go for secondary memory or you go for the disk storage. By default, it is always the disk because secondary memory may or may not exist on your computers. So how does it hamper the performance? Let's say localization actually works if you have a serial file. If you are reading from a serial file, in that case, there are localization algorithms in the operating system which would be reading ahead of time. So if you are accessing A, B, C, the algorithm would predict that you are going to read D next. So it would try and fetch D, E, F, G values into the cache. So whenever the CPU needs those values, you will not have to do a round trip to the disk again. You would find it either in the RAM or in the CPU cache. So even in our case, let's say if you're working on an operating system, now in any of the operating system, whatever the free RAM is used, whatever the free RAM is, it is generally used for caching purposes. So let me show you my RAM calculation here. Okay. So if you see, the total RAM is 12 GB, out of which 4.1 is in use, 7.5 is available, and out of the available 7.5, 1.4 is cached. If I increase the number of virtual machines running on my computer, in that case, the cached memory would keep on increasing. It does not mean that it is eating up the free space. It is not calculated into the free space or available space. Out of the available, it is going to be 1.4 as cached. If you reduce the number of available GBs, in that case, the cached GB will also keep on reducing. So it is a flexible kind of setup that the operating system uses. So it would be using the RAM for caching purpose also inbuilt. So you don't have to worry about caching it all manually. Of course, we do some kind of caching for the processes, but that is not considered here in the caching part. What it means that it tries to extend the CPU cache. That's what the only benefit is. Now you know that primary memory is faster. It's very very fast than the disk storage. So there are concepts like virtual memory or swap space. In Linux, we would be calling it as swap space. In Windows, we would be calling it as paged memory or virtual memory. So whenever your memory size is limited, primary memory size is limited, and still you want to fit in a process that would take large amount of memory, but currently you're not able to allocate that all in primary memory, you generally extend the primary memory to the secondary disk storage. It acts as a RAM, but it is not as performant as a RAM because eventually the data is going to be stored on the disk. And every time you have to write something or read something, disk latency comes into picture. So now this concept here in Linux is called swap space. If you think that your primary memory is performing too slow, the process are not getting proper resources, in that case, this might be the place where you want to check. Okay, so currently in my case, it says that my swap space is 0, and this is what the ideal statistic should be. Swap space usage should always be 0. If your swap space usage is increasing, that means either your process is eating a lot of memory than it is expecting, or you really have the problem of memory. In that case, you'll have to increase the memory. Okay, so current memory allocation to my computer is 1 GB, out of which 1 GB is again a swap. So total memory which would be considered as primary memory is 2 GB on my computer. 1 GB is RAM, another 1 GB swap space, which is actually the disk, out of which 121 MB is used. Okay, fair enough. All other is empty. And since the primary memory is empty, it is not pushing anything to the swap space. Whenever your primary memory is full, only in that case your swap space would be used. Okay, makes sense. So if you think that your swap space is getting used very frequently, in that case you'll have to increase your primary memory or figure out the processes which would be eating up more of the resident memory or the virtual memory. Here in this case, the fourth and the fifth column. Okay, it would also show you the percent memory that the particular process is using. So if the process is a user process, just like in case of Docker, when we have seen that the processes are able to use or utilize all the resources on a machine, since we go with uh, sorry, not optimized, it's called optimistic approach of allocation, resource allocation. In that case, we think that the OK process would be taking up only the resources that it's requiring. But just in case if the process is leaking memory, or it is trying to open up a lot of files but not using them, creating a lot of variables without eating them up, or the variables going out of scope, if everything is running in global scope, in those kind of things, you will run out of RAM very soon. Okay, so you will have to take care of these concepts based on the application that you are trying to execute. So there is no specific statistics for either CPU or registers or primary memory. You'll have to try and figure out the things yourself, but I'm just navigating you through these concepts so that you at least know that these could be the problems and you need to figure it out. It is very specific to applications and changes values between two companies and two different projects. Now the third part here, apart from memory, would be the disk. We have known about the CPU scheduling, the different algorithms which are present there. Similarly, disk also has got disk scheduling. So there would be algorithms on disk side as well. Okay. Uh, there is a nice algorithm called Noop. Then there is a priority algorithm. Another one would be the FIFO algorithm, first come first serve basis. So the best one here is actually the round robin, that gives every process a fair chance. But in that case, near real-time processes would be hampered actually, because let's say there is a real-time process coming in, waiting for the disk uh, to process its request. But since disk is a passive resource as in it does not execute the things itself. Someone has to trigger it. After the trigger or the command being received, disk will go fetch the data and finish the operation. Okay, that's what it is. That's why it's called a passive resource, not active resource. Servers are always active, so they would be always on. They are not waiting for anything to happen. They would be waiting for the request rather. Or the background processes, they are taking care of the execution themselves. Okay, they would not be waiting for any of the users to trigger them. Disk is rather a passive resource which is waiting on a few processes, and the processes would be scheduled. So let's say there are 10 processes waiting. First one is just finished, and the 11th one which comes in is actually a high performance system, so which would be having a lesser nice value, and you need to give it more priority. Then in case of FIFO or in case of round robin, you wouldn't have that. The throughput gets hampered. The waiting time for that process which is on high priority still is going to be the same, which is multiplied by 10 times the slots that you have. So what we do is we pick up the priority algorithm, in which the processes with the more priority or less nice values would be scheduled first. Okay, scheduling is fine, but there are a few things that has to be taken care. Very first is the read write latency. So the read write latency is due to the physical head that runs inside the disk, and more often that is the problem. So the if the head doesn't rotate, let's say over the disk very fast, in that case your read write speeds would be hampered. Again, another concept is that the spindle speed inside the disk. So disks that you would be generally using are going to be the magnetic disks. So since those are cheap and market these days, people are also using the SSDs, but that is not a culture these days. Someone who wants to have high performance systems on a specific section of the data center, only then they would be using some SSD kind of storage. Rather than that, every disk which is available in market is a magnetic disk, preferably. If it is a 1 TB disk or a 4 TB disk, doesn't matter. Now you see that when we are talking of 4 TB or 1 TB kind of disk, the space is increasing. Okay, so the data that we fit in per inch or per centimeter of the disk space is more compact. Okay, so compactness increases, the density of data increases, and that's when your arms, that means the head arms which moves over the spindles, has to be very accurate. If it is not accurate, it would be having some bits problems to that. So the disk will have to make round trips very frequent. So the first time it reads, it's not proper, it goes again and reads it back. So these things happen more often. That the spindle speed that we are talking, it is going to be either 5400 or 7200. So there are no more variations into that. We don't have spindle speeds exceeding more than 10,000 rpms available in market. So there is a limitation to every of each one of these. So you'll have to take care during creating the processes or applications that they do not make round trips very frequently to the disk. Now that is another reason why we use centralized logging using rsyslog kind of applications. And rsyslog, what happens is whenever you try to write to the disk, the log, when you're trying to dump the logs to a disk, in that case we don't wait for the disk. We don't write to the disk directly. Instead, we hand over the logs to some system like rsyslog. No, so RCS log would be taking care of gathering all the logs, and whenever the disk is free, RCS log would be dumping all the gathered logs at once. So let's say if you are on a machine which is receiving uh, 2000 connections or 3000 connections per second, so there would be 2000 different logs getting dumped. That's not a good sign. You'll have to make 2000 trips to the disk. Okay, so either your CPU would be strained because of that, because it has to switch so fast, and all the processes which would be logging to the disk, CPU would be switching them, and on the waiting side it would be triggering the disk again. So actually your response time for the particular process, so it is about the CPU, it is juggling between the processes, it is fine, but the total time which is taken up by one single process to finish, it would be determined by how many context switching happens, how many times it is provided a chance to execute itself, and how much time it is wasting on the waiting part of it on the disk. So this total time is actually the complete response time that you get on a particular process or a request on that slot. So use daemons for logging. So this is what is the takeaway from it. Do not rely on disk a lot. Do not log locally. Okay. So remove all the local logs to some centralized machine so that you send the data over the network instead of logging it to the local disk. Now, when we say that send the data over the network would be having its own problems. Network has got specific bandwidth. So maybe you are connected with a 100 Mbps line between the machines. And if you want to send the file which is bigger in size, maybe you have already generated a 1 GB log on one of the machine and you want to send it across. So is it possible that you use 100% of the bandwidth which is available? Of course not. If you use 100% of the bandwidth, then other machines who are trying to connect via that same network will not get their share of network bandwidth, and some problems might arise. The problems could be something like this: that you're trying to send the logs from your web servers. So there are some web servers present. Like these, you have got hundreds of different web servers on your network, and all of these web servers are able to talk to one another, of course. So we are not having various subnets created here. There would be one single subnet. All the servers would be able to talk to one another. uh, there would be a load balancer which is taking care of distributing the traffic. Okay, so traffic moves like this from load balancer to web servers, and the data that you want to collect, the logs that you want to collect, you'll have to collect it from the web servers themselves, right? So if all the web servers would be sending the data to one single log collector or centralized logging system, so we would call it central log server. Now you're running a very high performant website. Okay, so there are 100 different servers. I'm just talking about 100. There are thousands and thousands of them in a particular cluster. So if there are 100 web servers and all of them are sending the data, their continuous logs to central log server, very soon the line which is connecting central log server to the network would heat up. It literally heats up due to high bandwidth usage. So if your bandwidth usage is 100 Mbps, and since all the servers are sending their data continuously, and you're having maybe 10,000 users, concurrent users online, then in that case, the 100 Mbps bandwidth would be clogged. Okay, and packets start accumulating. So actually, the structure is not like this. Um, you'd be having. Let me show you how it is structured. We'll have to get through some devices. So there would be a device inside. Okay, so there might be multiple switches. Your cables do not connect to the machines directly. There would be some switches in between. Either it would be physical switch in the network, or it would be the rack switch that connects to the different machines inside the same rack. Now after the switches, you have the machine. And of course in between as well, that means whenever we say that web servers are connected, web 1, web 2, there might be switches in between, and every machine is connected to one single common switch. So the log server would be a part of maybe some second switch. And if there is another machine connected to the switch as well, okay, so switch 2 also connects to database. In that case, if all these machines, 100 different web servers, are trying to connect to the log server, in that case they would be clogging this line at switch 1. Switch 1 connected to switch 2, again it is 100 Mbps line, and the data that is flowing through switch 1 and switch 2, it's using the complete 100% of the bandwidth which is available. Now at the log server end, it may or may not be capable of reading all that 100 Mbps data, because the disk space, or sorry, the disk capacity generally on the spindle based rotational disks is limiting. It falls somewhere between 40 to 50 Mbps uh, in a routine 5.4k of RPM speed. If it is more, in that case it would fall somewhere between 60 to 80. So if that is the limitation and you are getting the data at 100 Mbps speed, well, I'm expecting that all of these are generating the data at 100 Mbps, just to be fair enough here. So 100 Mbps line is taking up all the bandwidth. It is coming to the log server. Log server is not able to read all of that, and it is reading it at the speed of 80 Mbps. So what happens? There is a buffer maintained with every operating system for a particular port. So when this buffer fills up, it would be filling up very pretty soon, because you don't have much buffer allocated. Generally, the buffer allocation is not more than 2 MB or 3 MB per port. Now you have a difference of 20 MBs. So the machine very soon gives up. It starts dropping the packets. So if a packet is dropped, in TCP connection, if a packet is dropped, then the source would not get the acknowledgement. Okay, so TCP handshake doesn't finish. Source would not get acknowledgement. So source a machine, whatever the web server is, it would be sending the packet again, and that keeps on adding the packets to the network. So very soon you will find that switch 2 is all congested with the packets. It's all flooded. Now when web server would try to make a request to the database, your database request will not reach the database, because switch 2 and switch 1, both of them are blocking the network through them. They are trying to push the log packets, and your legitimate web requests for the database access would be all blocked. So you think that the database is down, okay, because you're not able to ping the database server. The clients would be getting the pages like, sorry, we are not unable to serve your request because the database is not working. Now everyone sees that there is a problem with the database in this case. There might be other support systems which might fail due to network congestion, but actually the problem is log server. So what you do, if you want to figure out these things, as soon as you kill the log server or you shut it down, any of the requests which would be present on any these switches for that particular IP, since the IP does not exist, the switches would be dropping the packets at their end itself. So the network congestion would reduce drastically. At the same time, within a few seconds of time, you will see that the network congestion is resolved. Okay, so these kind of things happen. The problems are due to limited bandwidth, the buffer level on the operating systems, okay, and inefficient architecture. So what do we do to fix this kind of problem? Very first, connect the machines with high performant lines. Maybe you use something like fiber optics or fiber channel cables rather than the 100 Mbps CAT cable. So in data centers, we don't have CAT cables used between the racks. We generally use fiber optic channels between the racks, so that the speed that we get is more. It would be very close to maybe 100 Gbps or something like that. Now, what about the log collector? Because this is eventually going to cause problems. Even if I connect the switch with the high performant fiber optic cable, switch would be having its own problems, so own limitations. So for that, what we do, we keep multiple log collectors. We don't keep one single log server. We say that, okay, web server and web server 2, or maybe even a few more machines, would be connecting to some different log collector. Okay, there would be another log collector in line. So there are multiple log collectors. Let's say we have one log collector getting the data from 50 different machines. So that has to be decided based on how much data you are sending, what is your network capacity, and what is the intake capacity of the log collector. If the log collector is able to read and write the data at the speed of 50 Mbps, then it makes sense to send the data only at the speed of 50 Mbps or less to that log collector. Usually, we do not try to exceed 85% of resource utilization. The same amount of resource utilization is almost 50%. So under it, it's awesome. If it goes beyond 50 to 85, then we consider that to be a warning sign. After it moves beyond 85, that's a critical sign and you need to take care of it as soon as possible. Otherwise, the machine would go down. So the log collectors would be collecting the logs from the pool of machines. So if you are sending the data from 50 machines to one single log collector, that wouldn't freeze the channels which are coming to the log collector. You would be still fine. Now the log collector connects to another machine, and this another machine is called the central log collector or centralized log server. And now at every level we could control the speed. The speed at which log collector 1 would be sending the log to centralized log server would be different than the speed at which these all the servers combiningly are sending the data to the log collector 1. Okay, so that has to be controlled. The servers that we use for this kind of channelizing of data is called rsyslog. So this is a standard in industry. There are other log collectors as well, other proprietary log collectors rather. You might use log collectors which are provided by the frameworks which are available in market, or tools such as papertrail or logstash would be helping you to send the logs from servers to their centralized log servers. So that's all up to you how what you use and how you set up, but this is a generic architecture that you should be using. Devices play a very important role. All the devices which work at network level are actually executing at layer 4 in the OSI model. So IP addresses, if they are the fake IP addresses or they are not proper IP addresses, then they would cause a problem. Okay. Your devices should be securely connected. The cables should not be loose. So that would also result in a packet loss. So even if the packet is received and if it is malformed, you have to drop it. Okay, and you'll have to request for another packet, fresh packet from the source. So that uses twice the bandwidth than it is actually required. Okay, so that's another problem here. Now, talking about the security part of your systems, how do we secure the systems? There are very few rules that you have to take care of. We don't have to be worried about the server hardening part as such. So there would be multiple things to configure there, but there is very simple stuff that we as DevOps people could do. Do not open any ports than required. Very simple thing. If you need port number 80 to be up because that's a web server, and port number 20 to be up because you want to connect to that machine from SSH, so 22 and 80 are only the two ports which should be open. Apart from that, all of them should be closed. Okay, so how do we allow this? We allow this using a firewall. We close all the incoming connections except for on port number 80 and port number 22. Again, Do not allow any unsecured connections. Unsecured connections as in connections without the password. That's what we prevent. We don't allow any users to connect to this machine and to debug the stuff unless and until it is really required. As soon as you grant the access, you'll have to monitor the access, and if they are done, kill the user from that box as soon as possible. Okay, no extra users, no extra processes. Then we do not allow root login via SSH. So whenever I try to connect to this machine, any of my machines, you would have seen that I try to connect using my user. I never try to connect using the root. Actually, the root logins are all closed, so I've configured that to not allow the root logins directly. The reason for that is if someone gets root access, that is going to be a problem. Maybe if you allow root login, then you don't know who is the user trying to connect to it, because all you would be looking at is a root user. And if the credentials are leaked, then maybe even the hacker who is trying to hack into your systems would be able to get the root access. But if you're trying to provide the access via some users, then you would be giving very specific access to that particular user. Maybe he is able to only install a package, or maybe he is able to only uninstall a package or change some files, but he is not having any root level access, so he will not be able to screw up the systems very fast. Okay, so that's another way. Then we say that allow sudo access only when required. Okay, and that also to a few commands. So you could grant access not to all, but to very few commands in SSH as well. So I'll show you the configuration files of SSHD and how they are setting up the things back then. So following all these simple things, you can prevent any of the unauthorized access to your box and convert that into a black box. A few more steps if you want to add, you would be logging to remote machine. Okay, prevent port forwarding. You don't want people to be using this machine as a traffic forwarding machine. What else can we do? um, okay, that would be it. So we keep a check on what's coming in. If you want to be that machine to be a complete black box, in that case you will not even allow the SSH access. Okay, so no one is able to connect to that machine even via SSH. Generally that is done for web servers, because web servers don't need to talk to one another, they would be running as standalone nodes. Okay, so in that case we don't use even SSH to connect to that machine. If it's malfunctioning, kill it, spin the new one. Okay, as simple as that. What about logs? Logs would be stored centralized. They would be sent across as soon as the log is generated. So you don't need to get to that machine in order to figure out what the machine state was. All right. So these are the few things that you will have to take care of during the security part of it. I'll show you where do we configure security for SSH and sudo. So for sudo, there the file name is etc sudoers. In this file, currently, the user that I'm running would be having all the access. When I type the sudo command, I'm getting access to all the different commands which are there. Okay, but instead of all the commands, what you could do is you could say that I want to provide access to only apt-get, because I want this user to be able to uninstall and install the packages. I don't want him to create users. I don't want him to change the permissions of any of these things. So give him the access rights only to apt-get instead of all commands. So that can also be done. Okay, we prefer this to happen instead of simply writing all and give access to all the commands and make him the complete super user of the system. Okay, so you would be adding the users here, like maybe I want to add some another user. and I want Jenkins to allow to change permissions on a few files and uh, services. So I would say give the privileges to the Jenkins only for the commands which are chmod for changing and changing the ownership, chown. Okay, so that is what would be there for the particular user Jenkins. So be very limited in what you are granting. Another one is for etc ssh daemon. So this is the file sshd-config. We could change the port, of course. If you want even more security, you could fool people by running your SSH daemons on some another ports, and people would be trying to figure out what's happening there. On the firewall perspective, there is a stateful firewall that you could set up, that if a person is trying to connect to a particular port and he's trying to connect to another port again and yet another port again, that means he is doing a port scanning. In that case, block that IP address. Okay, so if you are having some incremental port scans happening, you could block the IP address permanently, or maybe for next 1 day or 2 days, whatever it is. So that could be done using the IP firewalls or IP tables firewalls, or even there is a another tool present in market which is called UFW. So depending on which product you use, you'd be having multiple features available. Go on and check for that. Here in this case, permit root login, do not permit it. RSA authentication, we are allowing that. Public key authentication is allowed. Then a few more things that we want to disable, like host-based authentication. It always has to be no. Host-based authentication is one when you allow machines to connect between one another instead of users to connect. So any of the user which would be present on machine B, if machine B is allowed host-based authentication here on machine A, in that case, any of the users who are present on machine B would be able to access machine A. We don't want that to happen. We want user-specific things to be present. So it is always considered to be no. Permit empty passwords is no. Nothing more fancy to be present here. On the ports, sorry, not the ports, the versions of SSH which are present in market, there are two different protocols being used, protocol 1 and protocol 2. So we are interested in the latest protocol, so it is protocol 2. Protocol 2 is also backward compatible. Okay, but just in case if you want to specify protocol 1, you could change it here. But make sure that all the machines who are trying to connect to one another would be using the same protocol for connections. A little bit about firewalls, that how do we set up the security thing. When I say that do not open any ports, close all the unsecured connections, do not make this machine to be a forward machine, or do not let people use this machine as a forwarding machine, then what do we do? Okay, so for that we use firewalls. So firewall is a software. Either it would be a software or a hardware, that depends. So there are two different kinds of firewalls, software based or hosted firewalls, or there would be hardware based firewalls. In the hardware based firewalls, of course you do have software, but that is called firmware in that case. And firewalls are responsible for checking each and every packet that is sent to your machine. And there would be three different levels of scrutiny or checking that happens. One is pre-routing, another one is routing, and the third one is post-routing. So these are three steps. In pre-routing means the machine is not, sorry, not the machine, the packet is not being accepted by the operating system. It is before acceptance. Before you send the packet to the applications, what has to be taken care of? That is in pre-routing. Once the packet has passed the pre-routing stage, then there is a routing stage. That means where you try to check uh, whether whatever you want to do with the packet, you check it at the routing stage. Let's say you want to drop it, you want to check which user it is, you want to check what URL it is coming from, and based on that you want to drop it or use it. You want to block some ports, so the port blocking happens at the routing stage. Then the post routing part, once the packet is checked with pre-routing and the routing, and even the applications might have been using it, so in that case you want to decide whether to forward it now to the applications or let this machine consume it. So if you want to do some forwarding kind of thing, then you do it in the post forwarding phase. Even the routing part, the load balancing part rather, that is done in the post routing phase. So you can have firewalls being treated as load balancers, not recommended at all, and we are not going to cover that part. Just for your knowledge, they can be used. So maybe there are different packets which are coming in out of the triplet or packets of three. You want the first packet to be routed to machine A, second packet to be routed to machine B, and third packet to be routed to machine C. But that cannot be done actually, because if you are having multiple packets of the same request, I want to send a file, the file is sent in packets. I would be landing up in fragmented file if I try to do load balancing using the firewalls. Okay, not at all recommended. So we'll see a few examples how to set up the firewalls on this machine of mine. Okay, so I would be using IP tables for that. The package that you would be installing is apt-get install IP tables. There is an, sorry, it's IP tables S. So this is installed on my machine. There is yet another application called UFW. Now both of them are famous here in the Ubuntu world. IP tables is available with CentOS and RHEL machines as well. So you could use IP tables to set up the things there on those boxes. So I'll show you a few rules that you could use to set up the IP tables on your systems. So let's do one thing. I want a machine to allow SSH connections, to allow HTTP connections, just two services to be running on that particular machine. So very first thing that you would be doing is first increase the font of it so that it becomes more visible. Okay. IP tables. Now IP tables is the command that you would be generally using for adding any of the rules. Now there are three different chains. Okay, so there would be an input chain, a forward chain, and an output chain. And on every single chain, you can implement a few policies. Currently, there are some policies set. Now these policies which are set are default policies and will allow any kind of traffic which is coming in or going out of your system, or people are trying to use your system as a forwarding machine. Even in that case, everything would be allowed. So if you see the policies here on all the three chains which are mentioned, input, forward, and output, the policy is accept. Okay, and we don't want that to happen. We want to limit the policies which are there. I don't want to accept all the connections which are coming to this machine. So how do I change it? Very first thing, you'll have to flush any of the data which is present here on your IP tables. IP tables -f would be flushing all the rules. Currently, even if you flush it, it wouldn't change anything on this side, because that's the default policy. Okay, so everything would be accepted. If there are any rules set prior to you setting up the firewall, in that case, if you flush it, then your policies would be set to all default. That means all except. Now I am going to set up the policies for each and every of the chain here. I don't want the machine to be used as forwarding box. I can allow output, or that means outgoing packets from the machine, because I can trust my processes. Okay, if you don't trust your processes, in that case you can block the outgoing ports as well, but not recommended. The input chains, sorry, in the input chain, the policy is going to be something like this. I'm going to allow any of the connections which are established currently, because this is a freshly installed operating system. Then I'm going to allow port number 22 specifically for SSH connections. Then I also need to allow the HTTP protocol to pass through the different ports. Okay, so the ports which are being used by Apache for using HTTP and HTTPS are port number 80 and port number 443. So let's do that. During setting up these rules, we can also say that I want to accept connections only from this machine. That can also be done. Let's say in case of web servers, we have seen that the web servers would be accepting traffic from the load balancer. If I want the web server to be a completely black box system, then I would say that okay, web server, you'll have to accept the traffic coming on port number 80 only from this particular IP address, which is the IP address of the load balancer. You don't accept anything which is coming in from any other direction. That can also be done. So I'll show you different examples of this. Very first, I'm setting up the firewall for accepting any of the currently established connections. The reason why I'm doing that, I'm currently on the firewall, sorry, I'm currently using the client to connect to that machine. If I block all the incoming connections right away, in that case, the client that I'm using, the SSH client, I will not be able to access the machine. I would lock myself out of the box. Okay, I don't want myself to be locked out. I want to fire all the commands and set up the firewall correctly. So this is what I would be doing. IP tables for chain input. You could also have it written in caps. Okay, on particular interface, ETH0 or ETH1, whatever you are using, if you don't want to mention the interface, in that case it would be implemented on all the interfaces together. Okay, for the state, where the state is, for the connection state, of course, where the state is established or related, the action that has to be taken is accept. So the packets which are coming in from currently established or related connections, all should be accepted. So this is what I need to add as the first line, so that I do not block myself out. Now I want to specifically allow the connections which are coming in from port number 22. So I would say IP tables. Now for incoming packets on the chain, port is port number 22 and protocol is TCP. And action is accept. Okay, so IP table says that on the input chain, for any of the incoming packets, so it is I is incoming packets whichever are coming in on port number 22, I want to accept them. Similarly, if I want to accept the connections from port number 80, I would be doing it dport 80, right? But I want to specify that the connections which are coming in from another machine only, which would be in the range of this 192.168.56.101 maybe. So if this is the machine, okay, and the subnet mask is the first 24 bits, so in that case, allow only this machine to connect to this particular port. Rest of the machines will be not accepted. They would be simply rejected or dropped. But if you want to specify the network instead of a particular IP address, you could also do that. Allow connections only from this particular network. do not allow from a specific IP address. I can allow a range of machines, but only specific to this particular network having the subnet mask as /24. Accept the connections from them, otherwise drop the connections. Okay, so if I want to establish this, I would be setting it up on a particular Ethernet port. So I would say allow it on the Ethernet port or interface ETH1. On ETH1, I have this network coming in. I don't want any external people to connect directly to the machine. Okay, so we are specifically allowing port number 80 on ETH1, which is in our case ETH1 is for internal connections. Again, similarly for port number 443, which is serving HTTPS traffic, we are allowing that. Okay, what else? We have allowed port number 22, port number 80, port number 443, but very specifically we have allowed it. Okay, we are very choosy about the IP address range and the Ethernet interfaces that we are going to use for that. Now I want to disallow all the connections which are present there. So we would be changing the default policy. Okay, default policies are overridden by the specific statements that you mentioned here. But apart from this, anything and everything should not be accepted, it should be dropped. So there are three different policies that you could set as default. One is accept, we are already looking at that. Another one is drop, and third one is reject. The difference between drop and reject is whenever the traffic or a packet is dropped, you will not get back acknowledgement, you will not get back the error report that what happened to the packet, why it is not being accepted. If it is rejected, you will send back a nice message that this packet is rejected because of so and so reason. So the default policies that I'm going to set on any of the production machine are not going to be the reject rules, because it would again increase the bandwidth usage. So we would be silently dropping all the packets. We will not be even responding back to other people. So if you are setting the things like this, your machines will not even respond to the ping. Okay, you can see them in the console. You can see them as the service is running, the machine is up, it is inside the cluster, but you will not able to ping that machine even. So if you want ping to be working, you will have to allow port ping on allow the port number 53. That's what the ICMP port is. So here, once you do all this, we are going to set up the default policy to drop IP tables, set up the policy on input. So default policies are set by -p. Input drop. How does the IP table look now? IP tables minus list or just capital L. It is listing it. It would take some time. Actually, it does not take that much time. It might be implementing the policies right away. So it says that the input chain is following the policy drop. All the packets are going to be dropped except the packets which are coming in from this network, okay, and have type HTTPS, that means port number 80. All the packets which are coming in from HTTP and in this specific network, except all the TCP packets which are coming in from anywhere if they are of type SSH, that means trying to connect on port number 22. Okay, anything which is established currently would all be accepted from anywhere apart from this machine. So it would be internal network or it would be external network, allow them. What about the forward policies and the output policies? For the output, we keep it as default, we keep it as accept. For the other ones, I would say set the policy for forward drop. Okay, then check IP tables -L. Now your forward chain policies are dropped, and if you want to save this, because when you restart the machine all your policies would be lost. Okay, so if you want to save it, you would be calling iptables save. So it would be saving all the data. So next time you restart the machine, you will not lose these rules. Okay, remember to save your iptables. So there are a few examples that you could be using for setting up the iptables. Not only these things can be done. Okay, there are a few more stuff. Let's say something like uh, I was talking about load balancing, right? But which is not at all suggested. So load balancing in the IP tables could be done at packet level. It's not done at the request level, whereas the load balancing that we do um, at the load balancer level, it is not generally done at the packet level. It is done at the request level. So every single request that is coming in would be routed through different web servers. So here in this case, I'll give you an example of how IP tables are used for packet routing. So the command would be something like this: IP tables, uh, apply the rules for pre-routing on a particular Ethernet. So I would choose Ethernet 1 internal for the protocol TCP for the D port 443. Again, that's the long command mstate, where state is new and the mode is nth counter. So for every counter starting with 0, for every triplet of 3 packets, send packet 0 to DNAT is actually a dynamic network translation, network address translation that we do. So forward all these things, that since it is being used as a forwarding mechanism, so we would be using DNAT and forward to destination whatever IP address you want to mention on port number 443. Now similarly, you could fire the commands changing, instead of every packet 0, you would be writing packet 1. So packet 1 would be sent to some another IP address if you want to. Packet 2 would be sent to some another IP address. There is no packet 3 because you are having group of just 3. You are mentioning every 3 and your counter starts with 0. So if the indexing starts with 0, 3 packets would be 0, 1 and 2. So you will have to take care of all these things. So it is not recommended at all to play with load balancing here with IP tables. Okay, if you are specifically working at a packet level, in that case you could do this. But generally in our cases, we are not playing here with the traffic, the packet level traffic, but rather the request level traffic. There would be a few more. Let's say if you want to ping from outside, since in our firewall we are not allowing ping as well, so I want to allow ping. So I would say IP tables for the input chain. We are going to allow the protocol ICMP. Okay, and specifically I'm going to allow the two kinds of requests that are present in ICMP. When it is echo and another one is uh, reply, that means request and reply. So let's say ICMP type echo request, accept all such requests, and in the output chain we want to allow uh, unknown protocol ICMP. It must be operating system specific in that case. Let me see. Okay, it must not be present on the these machines. In Ubuntu, we have got it in uh, sorry, on CentOS boxes. So for this to work here in Ubuntu, we could do something else. IP tables, a input. So protocol, we would be using a TCP protocol, and D port we are mentioning specifically port number 53. J accept. So that would work. And on the output port as well, we are going to specifically allow that output. You don't need to allow it currently because we have allowed all the traffic out. But just in case, if you are blocking the output, you will have to uh, implement this as well. So your IP tables would look something like this. Remember that when you are blocking the connections from all the Ethernet ports for input, at the same time you'll have to allow the connections from the loopback address. We don't want the internal process to be blocked. If process A and process B, both of them are running on the same machine, in that case, I want to make sure that the processes would be able to communicate with each other, whatever port they are using, right? We don't want this process to be blocked. For that reason, I would be adding a new rule here, which is IP tables allow all the connections from the interface called LO, which is localhost, accepted. Similarly, for output on localhost, accept all the connections. Now, there might be a case when you want to use your machine as a gateway. So you know that the gateway machine is responsible for allowing machines to access the internet. Okay, so for that you'll have to make sure that the connections which are coming in from the internal network are allowed externally. So the port forwarding is there, but of course there is a lot of scanning happening. You'll have to enable the packets which are coming in from internal network to external network. So for these things to happen, you could set up the stuff like this, where IP tables -a. Now this time forwarding, anything which is coming in from ETH1 should be allowed on ETH0. In our case, ETH1 is host only adapter. ETH1 is the NAT adapter which allows us to connect to the internet. And I'm allowing the packet flow between these two. Okay, so that would work. If you want to, yeah, there are a lot of things that you could do actually. That blocking POP3 or blocking MySQL, preventing access from unauthorized IP addresses and so on. There is one important one. That means if you want to block a particular IP address, that's what I was talking, that if you want to block a IP address, if it is doing some port scanning, so what has to be done? Or even more generic, if you are being targeted by a DDoS attack, okay, or a DOS attack, and there are multiple packets which are coming in at the rate that you do not expect, you want to block all those particular IP addresses, you could do it like this. IP tables, of course they would be in the input pipe, TCP port number 80. You could also block it on port number 443 if you are using it. Now the mode is limit. Now we are not using mode as state. The limit 25 per minute. If you are getting anything more than that, start the tracker. And if at once you receive more than 100 packets or requests coming in that case, block it. Okay, so more than 100 would be blocked. less than 25 would be allowed. So this rule is for acceptance. Okay, so now it works. Deport 80 mode is limit, where limit is 25 per minute. It's allowed. Apart from that, if the limit burst is 100, it goes beyond that, do not allow it. So acceptance criteria is for 25 requests per minute. In your case, if your server is allowing, maybe is capable of serving 100 requests per second, that's rarely not possible actually, unless and until you are serving static requests. If you're running dynamic requests, then each of the requests would be taking at least a few milliseconds to execute rather. So you cannot have 25 maybe 100 per second or 200 per second kind of ratio there. So depends on what your application is, how do you define the performance for that. You'd be setting up these values. Okay, but the rule should help you in blocking any of the DOS attacks that would be coming in. So depending on your server capacity, you would be setting up the values. That's what I meant. Okay. There would be a lot of other examples depending on your use cases, but I guess you have got a fair idea of where we could play. We could play with the source networks, source IP addresses. We could play on the Ethernet cards by passing -I and -O as the NIC card addresses. Which one do you want to block? Then the policies you are going to set up on different chains. Okay, sorry. So there is input chain, forward chain, and output chain. So these are the concepts where you would be setting up the rules. Apart from these, uh, there would be a example. There would be multiple examples which are available online as well. So depending on your use case, you might use it and work around things. So that is the firewall concept that I want to cover. Uh, Again, save it. IP table save. If you are on CentOS boxes, you'll have to save the IP tables like this. You'll have to go to init.d. It is present here or it's present to some other location. Um, it should have been present here. Okay, that's on CentOS machine. Sorry for that. On CentOS machine, it is going to be initd slash IP tables, and the command is going to be save. Okay, you don't type in IP tables minus save on CentOS boxes. Here on Ubuntu systems, you type it like this: IP tables hyphen save is a command that would be helping you to save your uh, IP tables. One more thing that you could do with IP tables is, if you do IP tables save, you could store it inside a file. Okay, so next time, even if you miss the save tables, if you flush them out, you still have got a copy of yours inside iptables.rules that you could load. So that's all about IP tables that I have to cover. If you have any queries or doubts, you may ask. Um, we'll be setting up these in the final class if you get time again. Okay, tomorrow we'll be covering up the next concept, which is a concept about the relational and NoSQL databases. Okay, when to use which, what are the use cases of relational and NoSQL databases, what are the points that you need to understand from DevOps perspective of it, that when to use which, what are going to be the architectural challenges when we use relational databases versus NoSQL databases. So this is going to be covered in tomorrow's class, and also we are going to touch up on a few Linux utilities that are used as regular DevOps day-to-day activities. Okay, something like top, htop, SSH servers, then SSL, OpenSSL protocols for hashing. So all this kind of things we will be covering in tomorrow's class. Any questions that you want to ask? All right, guys. So we could drop the call. If anyone wants to stay to discuss something, please stay. I would be talking to you. But apart from that, we are done for the day. We will be meeting again tomorrow at the same time with a new concept. Thank you so much for attending the class today.